caught me early here.
No
All right.
worries.
So anyways, the sine of 2 times A is equal to 2 times the sine of A times the cosine of A. This is called a double angle identity for the sine function. You know, in reality, ladies and gentlemen, this is used quite a bit. I've noticed this is used quite a bit in calculus and also even in physics. If you take a course in physics, you do stumble across this identity when you start working with vectors. In velocity is a vector in 2 dimensions. Or even 3 dimensions. And so this identity does come into play when working with components of a velocity vector in physics. All right, so what we have here is the double angle identity for sine. This is a useful one. Okay, so we'll lock that away in our memory banks. Let's now try another one, try to develop another one. If I take the cosine of 2 times some angle A, let's try to develop the double angle identity for the cosine function now. Well, the cosine of 2A can be rewritten as the cosine of A plus A. And now we can expand this out using an identity we seen yesterday. Recall, yesterday, the first identity we seen in 5.2 was the cosine of the sum of 2 angles is equal to the cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. This was a valid identity from yesterday, and we can make use of this identity to help us expand this out. So therefore, this expands out into the cosine of the first angle times the cosine of the second angle minus the sine of the first angle, which is A, times the sine of the second angle, which happens to also be angle A. When we simplify this, cosine A times cosine A is better known as cosine squared A. Sine A times sine A is sine squared A. And ladies and gentlemen, what we have developed here is we have developed what's called a double angle identity for cosine. So we have another identity to put into our toolbox. So therefore, in general, the cosine of 2 times some angle, maybe theta, is equal to cosine squared of theta minus sine squared theta. This is a double angle identity for the cosine. There are 2 other equivalent versions for the double angle identity for cosine. And the 2 other equal versions come from us using the Pythagorean identity and replacing either cosine squared theta with its equivalent result, or replacing sine squared theta with its equivalent result. So I'm going to derive now the 2 other equivalent forms for the double angle identity for cosine. First of all, any questions about what's going on this page here? Are we getting this accounted for here? So we've developed 2 identities this morning, double angle for sine and a double angle identity for the cosine. All right. So double angle formulas this morning in 5.3. All right. Taking this double angle identity for cosine, ladies and gentlemen, we know from the Pythagorean identity, we know that another name for cosine squared theta is 1 minus sine squared theta. Correct? That comes from our Pythagorean identity we seen a long time ago. So in place of cosine squared theta here, I can replace put in 1 minus sine squared theta. So 1 minus sine squared theta can substitute in place of cosine squared theta. In which case we'll have cosine 2 theta being equal to 1 minus sine squared theta minus sine squared theta. And we have yet another form for our double angle identity for cosine. The cosine of 2 theta is also equal to 1 minus 2 times the sine squared of theta. So this is another equivalent form for the double angle identity for cosine. Cosine 2 theta is equal to 1 minus 2 sine squared theta. This is equivalent to this version of the double angle for cosine. And I could have, instead of replacing cosine squared theta with its equivalent, I could have replaced sine squared theta with 1 minus cosine squared theta. Because from our Pythagorean identity, we know this is true. So replacing sine squared theta with 1 minus cosine squared theta, another version for the double angle for cosine is to say that cosine 2 theta is equal to cosine squared theta minus quantity 1 minus cosine squared theta. So cosine 2 theta is equal to cosine squared theta. We could distribute the -1 inside the parentheses here. So we'll have cosine squared theta minus 1, and a minus cosine squared theta is a plus cosine squared theta. And so we're going to have cosine squared theta plus another cosine squared theta, which is 2 cosine squared theta minus the 1. So here is another equal version of the double angle identity for cosine. So the double angle identity for cosine comes in 3 flavors, if you will. This identity, or this one, or now this one. They're all equivalent to each other, though. Okay, just different versions of each other. All right, any questions about what just happened on that page there? Okay. So now we have developed the double angle identities for the sine function and the cosine function. And using these identities, of course, we can derive the double angle identities for all of our other trig functions. The tangent, the cotangent, the secant, and the cosecant functions can all easily be derived by knowing these double angle identities for sine and cosine. All right, so this page is accounted for here. So double angle identities. Well, let's derive the one for tangent now. If I got the tangent of 2 times some angle A, we know that's equal to the tangent of A plus A. Now, to derive this identity for the double angle for tangent, you could do it one of 2 ways. You could use a ratio identity and say the tangent of 2A is the sine of 2A over the cosine of 2A. I mean, that'll work. So we could say this is equal to the sine of 2A divided by the cosine of 2A. But we've already developed the identities for the double angle identities for sine and cosine. So therefore, the numerator can be replaced with 2 times the sine of A times the cosine of A. And the denominator can be replaced with one of 3 versions of the double angle identity for cosine. I mean, take your pick. It can be replaced with cosine squared A minus sine squared A. All right, could be replaced with that if you want. That's one version. Or you can replace the denominator with 1 minus 2 sine squared A. Or you could replace the denominator with 2 cosine squared A minus 1. So the tangent of 2A is either equal to this guy here or is equal to this here. These are all valid identities I'm boxing in. Or the tangent of 2A is equal to this one right here. So these are all valid identities for the double angle for tangent. Or, ladies and gentlemen, you could use the identity from yesterday. Recall that the tangent of A plus B in general is going to be, how does this identity work? Do we remember from yesterday? I think it's the tangent of the first angle plus the tangent of the second angle divided by 1 minus the tangent of angle A times the tangent of angle B. Do you agree? We ran into this one yesterday. That's a valid identity we established yesterday. So using this identity, we could have also derived the tangent of 2 times an angle A, which is the tangent of A plus A, which is the tangent of A plus the tangent of A. Divided by 1 minus the tangent of A times the tangent of A. So in reality, ladies and gentlemen, although these are valid versions of the double angle identity for tangent function, the most popular one that is used is this one here. The tangent of twice an angle is equal to 2 times the tangent of that angle divided by 1 minus tangent squared of that angle. This is the identity you'll see in most textbooks for the double angle identity for tangent, this one here. However, this identity is equal to any one of these. This one, and this one are all equal to this one here. I know it doesn't look like it, but they are. This are all equal to this. And you know, a good exercise, ladies and gentlemen, if you want to challenge yourself, is to show that this right side here, is to show that the right side of this is equal to this down here, or to show the right side of any one of these is equal to 2 tan A over 1 minus tan squared A. A good exercise to show or prove that this or this is equal to this, because they have to be. Okay. But this is the most popular version of the double angle identity for tangent function, right there. Okay. All right, so the ones I wanted to derive here this morning were double angle identity for the sine function, the cosine, and the tangent. The other ones could easily be derived based on what we know with these here. For instance, if you wanted to derive the secant of twice an angle, the double angle identity for secant, well, we know the secant is the reciprocal of the cosine function. And so the secant of 2 times A is 1 over cosine 2 times A. Well, what's the cosine of 2 times A? We have 3 different versions for that. So one double angle identity for the secant of twice an angle is 1 over cosine squared of that angle minus sine squared of that angle. Or you could replace this denominator with those other 2 aforementioned versions. The cosecant, the double angle identity for cosecant. Cosecant of twice an angle is 1 over the sine of the twice an angle. But we've already developed the identity for the double angle for sine. So this can be rewritten as 1 over 2 times the sine of angle A times the cosine of angle A. You see that, how we can derive the other ones here by using the ones we know. The cotangent of twice an angle is 1 over the tangent of twice an angle. But ladies and gentlemen, we just developed the double angle identity for tangent. This is the most popular version of the double angle identity for tangent. If you just basically reciprocate this, you'll have the cotangent of 2 times A. So just flip this fraction upside down. So therefore, this is going to be 1 minus tan squared A over 2 tan A. Okay, so there's the double angle identity for the cotangent. All right, so there you have them, all the double angle identities for the 6 trig functions. Now it's just a matter of, employing these and taking care of business, as they say. All right, any questions about any of those identities so far this morning? The double angle identities for our 6 trig functions. All right, let's go to our textbook, section 5.3. Of course, you're always welcome to look over the sections and encouraged to do so. Anything in a yellow shaded box is an important concept. I think you've gathered that by now in your textbook. Always wise to maybe look over some of these examples your author's working out. By doing all this, it can only solidify your understanding of what's going on if you pair that with what it is I am saying during class, okay? All right, so let's go down here. The problems begin here on page 269, I believe. All right, so page 269. Let's look at number 1 here. This statement blank an identity sine of 2a is equal to 2 times the sine of a. Is that correct to say that, later on? Sine of 2 times a is equal to 2 times the sine of a?
No, that's false, right?
That is false, because what we've seen here is if you got the sine of 2 times a, the sine of 2 times an angle is equal to 2 times the sine of that angle times the cosine of that angle. This is a valid identity, so that's false. So problem number 1 on your textbook on page 269 is false. So this statement is not an identity. This is not a valid identity here, okay? Number 2, this statement blank an identity, cosine of 2 times an angle theta is equal to cosine squared theta minus sine squared theta. Is that true? Is that one of the valid identities we've seen this morning? If you look back in your notes, is this a valid identity for the double angle for cosine?
Yes.
And you can see that, yes, it is, right? Cosine 2 theta is equal to cosine squared theta minus sine squared theta. That's one of 3 equivalent versions for the double angle identity for the cosine function. So that's a valid identity there. All right, so this statement is an identity. Number 3, cosine of 2 theta is 1 minus sine squared theta. Is that a valid identity? Is that a valid version of the double angle for cosine? 1 minus sine squared theta? Well, it's close, but not exactly correct, because the cosine of 2 theta can also be shown to be 1 minus 2 times the sine squared of theta. So that is not valid to say that that's an identity in that problem number 3. That is not a valid identity. Finally, number 4, the cosine of 2 theta is equal to 2 cosine squared theta minus 1. Is that a valid version for the double angle identity for cosine? 2 cosine squared theta minus 1. We have certainly shown that cosine of 2 theta is 2 times cosine squared theta minus 1. So that is a valid identity for the double angle of cosine there. All right, so that's valid. Okay. Well, let's see here. Let's try a problem now. Problem number 2. They indicate that the sine of some angle A is to be the ratio -3/5, where angle A is to be between 180 and 270 degrees. Then they want you to find the cosine of 2 times A in problem number 2 here. I have a question. What quadrant would angle A be in?
Quadrant 3.
Yeah, quadrant 3. is where angular measurements are between 180 degrees and 270 degrees. So they want us to find the cosine of 2 times A, knowing that the sine of angle A is equal to -3/5. And notice further evidence that angle A is in the third quadrant is the fact that the sine of that angle is a negative ratio. And that's certainly true in the third quadrant where your y coordinate's negative, correct? Your y coordinate being equal to the sine of the angle of the unit circle. Okay, so how are we going to find cosine 2A? Well, we use the double angle identity for cosine, and there's 3 different versions of this. Take your pick. Now, I have a question for you, ladies and gentlemen. Based on what they tell us, what would be the wise version for the double angle identity for cosine? Based on the fact that we know the sine of angle A, which version of the double angle identity for cosine would we probably want to use? The first version, the second version, or the third version? What do you think? Based on the fact that we just know the sine of angle A.
The second.
Yeah, the second version would be the way to go because that only involves the sine function. I mean, you could use the other versions, but then you're going to have to find the cosine of that angle A first. Let's use the second version. So therefore, cosine of 2 times A is known as 1 minus 2 times the sine squared A. So we have 1 minus 2 times. Now to say sine squared A is to mean that we square the sine function. We don't square the argument of the sine function, we square the whole function. So therefore we have 1 minus 2 times what drops in for sine A? Well, -3/5. And then we are to square -3/5. So this is going to be 1 minus 2 times, now -3/5 times -3/5 is, on a good day, is 9/25. Now it just comes down to basic math. We have 1 minus 18/25. 2 times 9/25, 18/25. Another name for 1 is 25/25. Minus 18/25 is going to give you 7/25. And that's your answer. So 7/25 would be equal to cosine of 2A. All right. Now, it's interesting to note that if angle A lies between 180 degrees and 270 degrees, and if you double angle A, that means the angle 2A must lie between 360 degrees and 540 degrees. Isn't that true? If this is true, this must be true. Okay. And 360 degrees to 540 degrees would be what quadrants? Just curious here. To be greater than 360.
Quadrants 1 and 2.
1 and 2, I believe, correct? Well, notice the cosine of angle 2A gives us a positive ratio. So this angle 2A obviously has to be in what quadrant? 2A has to be in quadrant what? What do you think?
Quadrant 1.
Yeah, it has to be in quadrant 1 because the cosine of this angle 2A is a positive ratio. So it has to be quadrant 1 because in quadrant 2, the cosine is negative. So just pointing that out. I mean, we don't, for this problem, really have to, be aware of that or deal with that. Our answer is 7/25, but just kind of pointing that out. All right. So that's one like number 2. And let's see what else. So number 2. Okay. Like I said, if you ever see a problem you'd like to see done, just let me know. Otherwise, I kind of pick and choose some key problems. One like number 12, they indicate the tangent of theta is 5/12. Theta is in the first quadrant, and therefore they want you to find the secant of 2 theta. the secant of 2 theta. Well, the secant of 2 theta we derived a double angle identity for the secant function. It's one of these 3 here. Whoops, excuse me, just this one. Well, there's actually 2 others, right? Because this is also equal to 1 minus 1 over 2 cosine squared A minus 1. And this is also equal to 1 over 1 minus 2 sine squared A. So it's either one of these versions here. These are all equal to each other. So you could go that route there. All right, you could use, make use of one of these to find the secant of 2 times your angle A. Could do that. Or another way to deal with that, since they give you the tangent of angle A, is to make use of a Pythagorean identity. The fact that the tangent squared of an angle A plus 1 is equal to the secant squared of that angle A. You could use this one too. So it's up to you. So for number 12, they do indicate that the tangent of angle theta is 5/12. And theta, they tell us, is the first quadrant angle. Okay. So that's what they indicate to us. All right. Now we know the tangent of theta is the ratio of the sine of theta to the cosine of theta. So 5/12. So another way to deal with this situation here is you could also imply then that the cosine of theta is equal to 12 and the sine of angle theta is equal to 5, correct? Isn't this true? So to find the secant of 2 times theta, like I said, you could tap into this identity here if you want, or we can make use of one of those that we derived. Secant of 2 theta being 1 over the sine of 2 theta. Wrong, that's not right. Secant is the reciprocal of the cosine function, right? 1 over 2 times, or 1 over cosine 2 theta rather. All right, so the secant of 2 theta could be 1 over, and you're welcome to use any version for the double angle identity for cosine. You could use this one, cosine squared theta minus sine squared theta, and go from there. So this would be 1 over, cosine theta is 12, so we're going to square 12, and minus the sine squared theta, which is 5, so we square 5. So it looks like, or appears, that the secant of 2 theta would be equal to 1 over 144 minus 25, which is going to be 1 over, what's 144 minus 25? Well, it's going to be, let's see, 120 would be 124, 120.
119.
119. So the secant of 2 times theta is 1 over 119. So there's a lot of ways to get the secant of 2 theta here. Many ways. You can use a double angle identity for cosine to do that, or you could use this right here, this identity here, to take care of that. Okay. So there's different ways. The bottom line is, whatever way you choose, you have to use a valid identity. That is the key. I mean, if you're not using a valid identity, then you're doing something else. Okay. All right. So one like that there. And that was one like number 12. One like number, let's see. It's the same type right there. Okay, let's see, number 18. We'll drop down to one like number 18 here. Express the cosine of 100 degrees in terms of the cosine of 50 degrees. Well, how are you going to do that? When you first read this, you're kind of scratching your head. Now, what's going on here? How can you express the cosine of 100 degrees in terms of the cosine of 50 degrees? What relationship? But after a little deeper thought, you start thinking about the relationship between 100 degrees versus 50 degrees. They differ by a factor of what? 100 degrees and 50 degrees. They differ by a factor of 2. So for a problem like number 18 here, the cosine of 100 degrees, do you agree, can be rewritten as the cosine of 2 times 50 degrees. We buy that there. Cosine of 100 degrees is cosine of 2 times 50 degrees. And ladies and gentlemen, we have a double angle identity for cosine. I mean, one version is cosine of 2 times theta is to say that this is equal to 2 cosine squared theta minus 1. Do you agree? That's one version of the double angle identity for cosine. Why did I not use a version that involves the sine function? Because in the instructions in problem number 18, they want you to express the cosine of 100 degrees only in terms of cosine of 50 degrees. They're not saying anything about sine 50 degrees being present in your final result. Because of that, I'm going to choose this version for the double angle identity for cosine. So we follow along here. So we'll have 2 times the cosine squared of 50 degrees. Notice 50 degrees, not 100 degrees, but 50 minus 1. And you can probably leave your answer like this, since they want you to leave your answer in terms of cosine 50 degrees. Well, that's what we have here. We have an expression in terms of cosine of 50 degrees. So this would be your answer to problem number 18. I would just stop there. Okay. That one makes sense how we use the double angle identity for cosine to help us out. All right, that's one like number 18, dropping on down. Let's see. Dropping on down to one like number 34. Now they're back into having us prove that trigonometric expressions are valid identities. And I'll tell you what, you wouldn't believe how many times, ladies and gentlemen, that number 33 and number 34 are used in calculus. They're used over and over again, especially integral calculus. You have to tap into these identities all the time. So these are important ones, 33 and 34. I'm going to do 34. I'm going to prove that the sine squared of theta is equal to 1 minus cosine 2 theta all over 2. Okay? But these are used all the times, like I said, in integral calculus. So number 34. Let's prove that the equal sign belongs in between the sine squared of theta and 1 minus cosine 2 theta divided by 2. So I have a question for you. What side would we want to work with, ladies? I'm on the right or left side? What side would you be tempted to work with? Bailey, what side do you want to work with, right or left side?
I would do right. Probably.
You're wise in choosing the right side. Yeah, you want to go with the right side here, ladies and gentlemen, because we have a double angle here. All right, and when you have a double angle, you always want to try to simplify double angles before you simplify just single angles. Okay, so let's go with the right side and try to show the right side is indeed the left side here. Well, here we go. The numerator is 1 minus cosine 2 theta. We have 3 versions for the double angle for cosine. I have a question for you. Which version would we want to use, knowing that our left side contains only the sine function? Which version would we want to use for cosine squared, cosine of 2 theta? Anybody? Which version would we want to use?
1 minus 2 sine squared theta.
Right down here, you see that? Because our left side only consists of sine theta, although you could use this version or this version for the double angle for cosine. Why? Because you're going to inject the cosine function into the picture, and that's a complication in our situation. So let's use this version here. So let's replace cosine 2 theta with 1 minus 2 sine squared theta. And I think you can start to see it coming together there already. We can see the sine squared theta is evident here. That's good. Taking the negative sign, distributed it inside the parentheses, we therefore have 1 minus 1 plus 2 sine squared theta. And that all sits over 2. These ones drop out of the picture, and we're left with 2 sine squared theta over 2. These 2's reduce. And ladies and gentlemen, we have clearly shown that the right side is indeed the left side for all angles theta. So that has been proven to be a valid identity. Like I said, this one's used quite a bit in calculus. Sine squared theta is equal to 1 minus cosine 2 theta over 2. For instance, ladies and gentlemen, if you're being asked to find the antiderivative of sine squared theta with respect to theta, if you're asked to integrate this function with respect to theta, this is very difficult to do. But just by using that identity that we now see in trigonometry, we can replace this integrand sine squared theta with 1 minus cosine 2 theta over 2. And then you can split this integral up. Since the integral is a linear operator, we can split this up in the antiderivative of 1/2 d of theta minus the antiderivative of cosine 2 theta divided by 2. This is a trivial antiderivative. This one's equally trivial now. Okay, you'll discover that in calculus. And so, ladies and gentlemen, to the rescue, to get us out of a very complicated situation in integral calculus, we make use of an identity from trigonometry. This is a very difficult integral to evaluate. This becomes a trivial integral to deal with. Okay, so identities can make your life so much easier when working with trig functions in integral or differential calculus. All righty. Okay. So we've proven number 34. Another one I wanted to kind of go over is one like 38. The sine to the 4th power of x minus cosine 4th power of x is equal to negative cosine 2x. They want us to prove that this is a valid identity, number 38. What side would you be tempted to work with here? For number 38. Right or left side? Unfortunately, trying to prove some assertions as being identities, your choice of what side to work with, ladies and gentlemen, could make or break you in some cases. And there will be times when you'll start working with one side and discover that it's just not going anywhere. Don't feel bad, it happens. All right. Sometimes you have to scrap an initial thought and then try something else. I mean, it happens all the time. Okay. Does anybody want to weigh in here as to what side you would probably want to show is the other side? What side
Left.
appear, yeah, you know, based on what I said earlier, normally we like to simplify double angles before single angles. This is a case, ladies and gentlemen, where you'd probably not want to work with the right side. Okay, you probably don't want to work with the right side. It's going to be difficult to show that we can get, you know, sine and cosine to the fourth power out of the right side. This is actually a case where you probably want to work with the left side and show that it's the right side. Okay, here again, it comes down to the fact that I keep alluding to and emphasizing. The only way you really get good at working with identities, improving them, is by doing a whole bunch of them. Because when you do a whole bunch of them, you gain a lot of experience. You learn, how shall I say it, the tricks of the trade. Okay. All right, so on the left side here, we're going to try to show the left side is indeed the right side. But where to begin? Anybody have a hint for us as to what we can do to begin on the left side? Anybody got an idea as to what we can do here? I'll give you a hint. It's something that we did in the past, improving another identity. Anybody remember the trick? See, that comes down back to experience now. Anybody remember what we did with a situation like this? Anybody recall?
Factor.
Factor. Thank you. Yes, ladies and gentlemen, it's very tempting to kind of view this as the difference between squares here. Okay. And from algebra, if you have like a to the fourth power minus b to the fourth power, if you got this binomial here, this would factor into a squared minus b squared times the conjugate binomial of a squared plus b squared. You see that there? So we're going to tap into what we learned in algebra now to apply to our situation here. Let's factor this left side. So therefore it factors into sine squared x minus cosine squared x times sine squared x plus cosine squared x. But one of these factors is trivial. Which one? Which one of these factors can be trivially simplified based on an identity we've seen in the past? Anybody? Which one?
It's a sine squared x minus cosine squared x.
Well, no, it's actually this one right here. What is another name for sine squared x plus cosine squared x? Anybody? Pythagorean identity, what's this equal to?
Isn't that 1?
1. This is 1, ladies and gentlemen, Pythagorean identity. So this factor is 1. So therefore we have 1 times sine squared x minus cosine squared x. So our left side collapses down to this. Now, how can we show that this is equal to negative cosine 2x? What were the double identity choices for cosine? We had this version, cosine of 2 times an angle is cosine squared of that angle minus sine squared of that angle. But we don't have cosine squared minus sine squared. We have sine squared x minus cosine squared x. What's the difference between this and this? The only difference is a factor of what? What's the difference, ladies and gentlemen? Only a factor of what differs?
-1.
-1, that's right. So look what we can do. We can factor out a -1 out of both these terms. And when you factor -1 out, you'll leave behind negative sine squared x plus cosine squared x, which is really -1 times, flipping these terms around, cosine squared x minus sine squared x. Aha. But ladies and gentlemen, another name for cosine squared x minus sine squared x, another name for cosine squared x minus sine squared x is cosine 2x. So therefore, this can now be replaced by the double angle identity for cosine with cosine 2x. And of course, we got the -1 factor out here, so the -1 factor remains. We have shown the left side is the right side for all angles x. Okay, so that is indeed a valid identity. So that has been proven. And to do that, of course, we had to know how to factor. And so that's why factorization skills are so important back in algebra. And that's why I always harp and stress on those things when I teach a course in algebra to my students to, become proficient. If nothing else, become proficient in your ability to factor polynomials. That's always a skill that comes back to haunt you in higher level math. Never fails, always comes back to haunt you in your calculus, your differential equations, anywhere you go, as I'm in mathematics, you're going to deal with factorization of polynomials. So that's a skill you want to keep strong. All right, that's one like 38. Problem one like number 40 is interesting. We have the cosine of 3 theta. Wow, triple angle. Huh. Cosine of 3 theta is equal to 4 times the cosine cubed of theta minus 3 times the cosine of theta. How would we prove that this is a valid identity? Number 40. What side, ladies and gentlemen, would you be tempted to work with here? Anybody want to take a guess? What side would we work with for this one?
Right side.
Okay, if you work with the right side, we're going to have to somehow show that this right side becomes cosine of 3 theta. Cosine of 3 theta. Have we ever seen cosine of 3 theta before? Have we ever seen that before? What we have seen, we've definitely seen cosine theta. We've today seen the cosine of 2 theta. We've never seen the cosine of a triple angle. Never seen that. Well, if you work with the right side, let's see, if you work with the right side, ladies and gentlemen, about all you can do on the right side is, you could factor out a cosine theta out of both these terms. When you do that, that'll leave you with 4 cosine squared theta minus 3. You know what I'm saying? That'll leave you with this. Is that going to help us go further, knowing this? This looks like a quandary, doesn't it? Doesn't look like, what are we going to do with this? You could use a version of double angle identity for cosine here. No, you can't. No, what am I saying here? That's not cosine 2 theta. So what are we going to do with this? This don't look good at all. This don't look good at all. Care to retract your statement, ladies and gentlemen? The right side does not really look like it's going to take us anywhere. Maybe we better go to the other side. Let's use the left side and show the left side is equal to the right side. So this is a classic example whereby we might dive in head first and jump on the bandwagon and thinking, well, it's the right side we got to work with. But the right side just does not, it's not leading in anything. I don't know how, we're going to be able to show that this is cosine 3 theta out of this. How are we going to do that? So this is a classic example to illustrate, yeah, we made a bad choice. Maybe we should go with the left side here. Well, that's just great. But what are we going to do with the left side? Anybody? What can we do with cosine 3 theta? What can we do with it? Anybody? I'll give you a hint. The way I derived a lot of the double angle identities today is what we could use here. Anybody remember what we can do? Cosine 3 theta. What can we do with it to get started? Anybody got an idea?
Could we set it equal to just kind of rework one of the problems to hold Hold for a second. Cosine. Oh, never mind. I lost it.
Okay. So you had some idea and it just bounced right off your mind. Anybody have any idea how we can get started on that left side? See, this is the toughest part of proving some of these identities that we face, like on a quiz or exam. Sometimes we don't even know where to begin. We don't even know how to begin with a side. And that's an awful feeling when you run into a situation like that, because you know the clock's ticking. Well, with our virtual setting here, ladies and gentlemen, time is not really a major issue on exams and quizzes. It would be in class though. You know, if you only had like an hour to do a certain number of problems, then you can start to feel the pressure of the clock. And that's when your mind can start to go blank. And that's a hellish place to be on a math exam. I've been there, done it. All right, ladies and gentlemen, any idea what we can do to get this ball rolling on the left side here? Cosine 3 theta. What are we gonna do with this? I mean, we've seen cosine 2 theta. We've seen cosine theta, but I mean, what can we do with this?
Can we break that down to cosine theta and cosine 2 theta?
You're getting warmer, on the right track. You're starting to think in the right direction here. Let's try to rewrite cosine 3 theta as the cosine. You agree? I can rewrite it as cosine of 2 theta plus theta. Do we all buy that? We can at least do that, can't we? Nothing wrong in saying that this is this. Now we're starting to move.
say that.
What's that?
It's like I was thinking it, but I was just too nervous to say
Okay,
it.
all right. Yeah, no, you're on the right track. Yeah, that's what you want to do. I mean, that's about all we can do here to move forward with this here. Just rewrite it, you know, cosine 3 theta, rewrite it like this. Now that we've rewritten it like this, we do have a sum identity for the cosine function we seen yesterday in section 5.2. And you remember how that identity worked there? Do we remember that identity? Cosine of A plus B was equal to, how does this identity go here? By the way, this is the one I'm going to show you the proof of. When I make the video, I'll probably be able to make it today because I'm not as busy today. So cosine A times cosine B minus sine A sine B. Do you agree we can tap into this sum identity for the cosine function from yesterday? We can apply it right here with this one. So therefore, let's expand this out. Our angle A is really 2 theta. Our angle B is really theta. So A gets replaced with 2 theta here and here. B gets replaced with theta here and here. So therefore, this is expanded out as cosine of 2 theta times the cosine of theta minus the sine of 2 theta times the sine of theta. So now we expanded it out. Now we're starting to move. We're getting the ball rolling here, ladies and gentlemen. Now look at this. Do you agree cosine 2 theta? We have an identity for that. In fact, we've learned there's 3 different versions for the double angle identity for cosine. Ladies and gentlemen, I have a question for you. Which version for the double angle identity for cosine would we want to use, knowing that we're trying to shoot for the right side, knowing that on the right side you don't see the sine function present anywhere? So what version for the double angle identity for cosine would we want to use? Cosine squared theta minus sine squared theta, 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta? Which version would we want to use to replace this guy?
The middle one, the
Yeah, only the one.
cosine.
Only the one with the cosine. Yeah, you want to use this one, 2 cosine theta minus 1. This is the version of the double angle identity for cosine you want to use here, because notice on the right side, we don't have the sine function anywhere. We only want the cosine function showing. So replacing cosine 2 theta with this, we have 2 cosine squared theta minus 1. This all has to get multiplied by this cosine theta function here. Now sine 2 theta. Unfortunately, the sine 2 theta, or the double angle identity for sine, it does have the sine function present. So the sine of 2 theta we discovered today is 2 times the sine of theta times the cosine of theta. So we have no choice, ladies and gentlemen, in replacing sine 2 theta with 2 sine theta cosine theta. All right, so 2 sine theta cosine theta. This has to get multiplied by the sine theta out here. Don't lose this sine theta. And we got it down to this now after expanding it. Okay. Distributing the cosine theta inside the parentheses. Wait a minute. Do I want to do that? Yeah, well, hold on. Yeah, I guess. Yeah, okay. So let's distribute the cosine theta inside the parentheses. So 2 cosine squared theta times cosine theta would be 2 cosine cubed theta. That's good to see because on the right side, we do have a cosine cubed starting to maybe come into focus here. Minus the cosine of theta minus 2 sine theta cosine theta times sine theta would be minus 2 sine theta times sine theta is sine squared theta times our cosine theta. So we got that. We got that. Well, that's great, you know, but how are we going to show that this, ladies and gentlemen, is this? We're getting a little closer, but still not quite there. Anybody know what we can do from here? What function here what function is it that we don't want to be present in our expression if we're trying to show the left side is the right side? Which one is the one we don't want?
Sine has got to go.
This sine function's got to go because we're trying to show the left side is nothing is equal to an expression only involving cosine functions. You see that there? We're aiming towards this. Ladies and gentlemen, we have to replace this with something, but with what? Can anybody tap into a previously seen identity to replace sine squared theta with something? Well, from a Pythagorean identity, we've seen that it is a well-known fact that another name for sine squared theta is 1 minus cosine squared theta. This can be replaced with 1 minus cosine squared theta. Here it is. All right, the good news is we have nothing but cosines on the left side now. No more sines. The bad news is this thing's like out of control here. I mean, this thing is like a nightmare right now. We have got to try to simplify this somehow. All right, so what are we going to do here? Well, I'm sorry, this was cubed. This cosine is cubed here to the 3rd power. Very important. Not the 2nd power, that's cubed. All right, so what are we going to do? Well, what we're going to do here is this. We have 2 times cosine theta, and that 2 cosine theta is going to have to get distributed into 1 minus cosine squared theta. So we're going to have to use our distributive property. This has to distribute into the 1 and also the negative cosine squared theta. We have to distribute. All right, so we have 2 cosine cubed theta minus cosine theta. Now, negative 2 cosine theta times 1 is minus 2 cosine theta. Negative 2 cosine theta multiplied by negative cosine squared theta will be positive 2. What's cosine theta times cosine squared theta? Cosine cubed theta. Aha. Ladies and gentlemen, combining some like terms now. What's 2 cosine cubed theta plus 2 more cosine cubed thetas? These add together to give you 4 cosine cubed theta. These middle terms add together 1 cosine theta minus 2 cosine theta is minus 3 cosine theta. And we're finally done with this nasty one here. We have shown that the left is the right. All right, so make sure you get that down, ladies. I mean, if you don't, even if you don't understand it 100% at this point in time, at least you know, can look it over in your happy place, wherever that is, and you know, slow the pace down and try to understand what just happened there. All right, so we've shown the left side is the right side. My happy place when I was in graduate school was always driving to a park in my car, rolling the windows down and doing my homework. That way I could enjoy the weather, the day, and I had complete quiet where I could concentrate and get my work done. I've done some of my best work in my car, ladies and gentlemen. That's no lie, too, no lie. You know, in graduate school, for a homework assignment for a weekend, a professor will give you maybe 3 problems to do. You're probably thinking to yourself, 3 problems? Mr. O gives us like 30 problems. How hard could 3 problems possibly be? Well, ladies and gentlemen, when you're in graduate school, those 3 problems can consume your entire weekend. You literally have to go online, nowadays online, but I had to go to the library and do research as to just to try to understand what it was I was looking at. I usually required about a day just staring at the problems, trying to figure out what it is I'm even looking at. And then the next day, I began to wade into the situation and try to do something with it. That's how difficult graduate school can be. Okay. All right. So be careful when a professor only assigns you 3 problems. Don't laugh at it. Don't laugh. All right. So that's one like number 40 there. In fact, my most difficult math class I've ever taken as a student was one where the textbook was a real thin textbook. It was my first proofwriting class I took at U of M Flint. And ladies and gentlemen, I fell flat on my face. I didn't even know what I was doing in that class. I couldn't write a proof to save my life. I had an opportunity to retake the class for graduate credit down at Eastern Michigan University. And then the light bulbs all came on. Okay. And it all made sense the second time. But be careful when you have a math class where the textbook's really thin, because a real thin math textbook means that your author left out a lot of examples and a lot of steps. And that's where you're going to be scratching your head for hours trying to figure out how they went from point A to point B. So you want thick textbooks that show everything. That's what you want. All right. So how did I get on this subject? Well, it's 10:09, ladies and gentlemen. I have a classwork for you. Today is August 4th already. Cruising right through summer. Hopefully you can still enjoy some of your summer before it's over. There's 2 problems. I want you to prove that the cosine squared of theta is equal to 1 plus cosine 2 theta over 2. This looks awfully familiar. Hint, hint. And number 2, if the cosecant of some angle beta, this is beta, ladies and gentlemen. It comes from the Greek alphabet. It's called beta. It's a common symbol used in trigonometry, although we haven't really used it a lot. We've been using theta for the most part, but beta is also equally used in most trig situations. If I tell you the cosecant of some angle beta is the square root of 5 and beta is a second quadrant angle, I want you to find the sine of 2 beta. Okay, go ahead and work on those problems. We'll come back and wrap it up. So we have a valid identity because the right side here has been shown to be the left side. Number two, we know that the cosecant of some angle beta, which is in the second quadrant, is square root of 5. I just built a little reference right triangle in the second quadrant. Angle beta, I labeled the sides of the right triangle. Remember, cosecant beta is the ratio of r over y. So r must be square root of 5, y must be 1. X must be -2 by the Pythagorean theorem. And therefore, the sine of 2 beta now using the double angle identity for sine is 2 times sine beta times cosine beta. Hence, sine beta takes on the ratio of 1 over the square root of 5. Cosine beta takes on the ratio of -2 over the square root of 5. Going through the arithmetic, multiplying that out, you get this. Did anybody get -4/5 for number 2? -4/5? Anybody at all? -4/5. Mark Brooks, did you get -4/5 for number 2?
I was still kind of like working through the problem. I didn't get the solution yet.
All right, anybody get -4/5 for number 2? Anybody? All right. These problems make sense to you?
I do. I think they make sense.
Yeah. All right. Did anybody do number 2 differently? Just curious. Anybody do number 2 differently and get the same answer?
I did it differently and got it wrong, so that's why I was just saying.
What did you try?
I went down the route of trying to figure out the cosecant, and then once I started going down that route, I realized I was really
Or
wrong.
were you trying to find out like using the cosecant of 2 beta? Were you using this right here somehow?
Yeah, or then I was trying to take that and then going from the where I realized I messed up was that I was trying to just make it 1 over sine of 2 beta. Then I realized that the cosecant needs to be 2a, and it wasn't. And so that's when I was like, okay, I need to go back and restart.
Just keep in mind, you can always build your right triangle, knowing in what quadrant an angle lies. And you can always label the sides of the triangle if you're given a trig value of that angle. So you can always, fall back to this. Something we've seen earlier, a lot earlier in the course here. So keep that in mind there. All right. That always works right here. Okay, so I will let you go and we'll wrap it up tomorrow. Now, look at the schedule. I think tomorrow, am I supposed to give out another quiz tomorrow? Let's see. August 5th. No, I'm not. No, there is no quiz I give out tomorrow. Now, Monday, August 9th, I will give the chapter 5 quiz out. So I will let you go, ladies and gentlemen. I'll put that proof of that cosine A plus B on Canvas for your optional viewing. Try to get the chapter 4 exam done for me by midnight tonight, and you guys have a great day. Hopefully I'll see you tomorrow.
Have a great day.
Yeah, have a good one.
All right, take care. See you. Bailey, do you have any